Okay, so today, hello, my name is Sean Cha. I'm a first semester PhD student in VML, and today I'm going to present deep deformable 3D caricatures with learned shape control, which was presented in SIGGRAPH this year in a conference track. And I brought this paper since it is very simple, but very interesting idea. So let's get started. For the contents, first I'm gonna briefly tell what the deformable model is, and then I'll tell the goal of the paper and the methods and the results. So first, what is deformable model? Do you guys have any guess? Maybe you guys can think just as literally some kind of a model that deforms into a certain shape. And that is kind of right, but not precisely correct for this, term. Yeah. So for the deformable model, it provides a parameter space that can move the shape of the model with the prior information. And for the very simple, for the simple example, though these are the deformable model, as I could say, which is 3DMM, which means 3D movable model, and flame and the simple model. So they provide certain parameter space that you could control those parameters to make the model deform based on the prior information, which is the learned data distribution. So the goal of the paper is very simple. They want to make this kind of parametric movable model, which can represent various types of 3D caricatures. So how did they do this? Now I'm gonna tell you in the method section. This is the overview of this paper. It is very simple and very easy to follow. So I'll just go by one. So first, before I go, never mind. So first, we have a template mesh, and we assume that they are trained with the various shape of the 3D caricatures, which has a point-to-point correspondence within each other shapes, which means their topology are the same, which has the same number of vertices, same number of faces in same order, but only the deformation is the difference. And so the input of this network is the point sampled from this template mesh, and which means the XYZ coordinate of the point. And given this XYZ sampled points, the network produces the delta of those XYZ. And from this delta, you add it back to the input coordinate, which is a given XYZ coordinate. And then you get the result of deformed 3D caricature shape. So it's basically generating a displacement for this 3D position of the mesh. So, and as you look into this overview, the network consists of two things. One is a hypernetwork and one is Siren. And you might not know what the hypernetwork is, so I will briefly tell you what this does. So let's say there's an orange space and a blue space, and you want to map the data from the orange space to the blue space. And let's say we have trained this network F that automatically maps the data in the orange space to the data on the corresponding data on the blue space. And let's say that function is ax plus b. And from that, we have we can make a we can automatically using this network to map all the data that belongs to orange space to certain points in the blue space. And based on this F network, you might want to move around within this mapped blue space. So I hope you guys see my laser pointer. So let's say I want to map this orange data to this blue data. And from the mapped data, you might want to kind of move around. You might want to kind of, let's say you want to make this blue circle into, maintain its identity blue color, but make it to like square or star. Then you might need to move around somewhere else. But since the network parameter is like fixed when it's finished learning, you cannot control, you cannot modify this relationship. So to kind of, no, forget that. Just let's say you know only the relationship mapping between this one and this one, and you want to move around somewhere else using this function. How would you gonna do it? Well, it's just simple that you, as I already said, that it is the F network is AX plus B. You can just change A or B into another number. Then you can make this blue spot into somewhere else mapped. And that is what the hypernetwork does. Hypernetwork is when some kind of arbitrary input is given, it outputs A prime and B prime, which can replace the A and B in the network A, F, and which might modulate the result of the mapping. Like this. So you can think the F is F defines certain direction to map the orange space into the blue space, and the H might be H has a responsibility of controlling this scaling or shifting in the space of the blue space. You know what I'm saying? Or maybe you guys might ask in the later Q&A session.
Okay, so I have a question here. So
yeah,
network is learned with the variation of A and B.
Yes.
Okay, that's the idea.
Yes.
Okay.
So the hypernetwork produces those kind of parameters for another network. And the Siren is also kind of a new thing for you guys, I think. So what is this Siren? To briefly tell you about what the Siren is, I need to tell you about the activations in the networks. You know, you might have heard of all those kind of activations like sigmoid or tanh or much more else thing. And you use that to make the network non-linear function. Because you need to, if you don't have an activation of non-linear function, that even though you stack all those layers of the network, it might also collapse into one single linear function. So you add a non-linearity to the network. And for the Siren, you just add a sine function as an activation. And that is all for this network. And also with a good initialization, they were able to kind of quickly converge and quickly learn to map a certain certain domain to other representation, continuous representation, like this example. As you can see, all other activations was take some time to converge, but Siren just 한순간에 해버렸습니다. 네. And yeah, by using all those 그 요소들, components, this is what it basically is. So simple. So for the training, they use this last function.
It is explain the latent part, the input hypernetwork.
For the latent code, it's simply Gaussian, sampled from the Gaussian distribution. So you can think of this as a generator, like the GAN network, the generator samples the latent vector Z from the Gaussian distribution and learns that distribution to be some kind of a data distribution, right? And this is what the hypernetwork does. So it generates some kind of, it learns some kind of distribution of shifting, changing this Siren parameter, which controls the shape of this morphable model. So back to the loss function. It is very simple mean squared error function between the ground truth point and the generated point. So H is a hypernetwork and Z is an m-dimensional latent code Z for kth training sample, which is sampled from the Gaussian distribution. So from this, you have a parameter, and using that parameter and the sampled point from the template mesh, you have the output of the displacement. And I believe this should be the plus sign, since you need to add those displacement to the base template position to have a deformed shape. And PI is the point from the ground truth 3D caricature mesh. So if you just subtract those two, you have those residual of the ground truth and the generated mesh position. And you sum it all up and divide to find the average mean square error. And this is a regularization term to make the sampled Z code not to be very large.
Wait, why it should be plus? You have a sampled points, and then you have a displacement that you add them together.
Yeah.
Then you take the difference with the PI, and there should be a parenthesis maybe. So it eventually it's minus.
아, 그렇구나. Maybe I have, misunderstood. Yeah, I think you're right. I think you're right. Okay, I think.
I have a question here.
Yep.
So, do the sampled points mean the positions of the vertices?
Yeah, that's a good question. They combine. They also use the sampled. They also use the vertex position of the mesh, and they also sample the points uniformly throughout the mesh, and they combine those two sampled points as input. So let's say there's some kind of a mesh which has like this 5 vertices. So they use these 5 vertices, and then they also sample another points uniformly like this. And they used this all vertices as a vertex position as a vector. I mean input. And to get this position, they use a varicentric coordinate to calculate the position. And yeah.
Then the points that are not the vertices are on the faces, or?
Yeah, there are vertices on the faces. So like, let's say there's a cube. Cube has 8 vertices, right? And you also can sample some uniformly on the surface of it. Yeah, that made pen be 8, so like using 16 of it.
Then does the sampled points from the ground truth and the result, does they have like a predefined correspondences?
Yes,
so that
yes.
You could subtract them?
Yes, yes. They are pre-calculated before the training, so it's a fixed points. Yeah, they all pre-calculated the correspondence between the template and the deformed GT meshes. Okay, so shall I continue?
Can I?
Yeah.
Can I have another question? I actually didn't get what this paper is doing. So could you explain one more time? So I don't get like what does the latent code or Gaussian random vector does to the output? and I don't really understand what is like the purpose of this. Is there like a target that we have to go to, or is it just randomly generating caricature mesh?
So it's you can simply think of this form as a generator that samples the latent code from the Gaussian and produces some kind of output. Like let's say you know, when you think of an image generator, then you sample the points from the Gaussian distribution and train this decoder to generate the output that may fit into some kind of image data you have, right? And this is exactly the same thing. You sample from the Gaussian points and you generate some kind of a parameter, and based on that parameter, make this network to generate various kind of 3D caricature that fits into the given data distribution. So you're training a
So where you explain the image synthesis part, I think you're simply explaining unconditional generative model. However, is this also like unconditional generative model? Because like if you see the loss function, you're comparing with the ground truth. So I don't think this is like the case here.
I think this is so it's a unconditional generator, I guess, but you want to make the network generate the output mesh that fits in the data distribution. So that's why I think they're trying to use the loss function directly. I mean,
and like, how do you have like a ground truth vertex value? Because I don't think there will be a correspondence between the Gaussian random factor and the meshes. So could you maybe explain that part?
correspondence between what?
So if you see the loss function, you're comparing with the generated ones and the what is it, ground truth mesh, right?
Yeah, right.
But however, if you think about it, if you're just randomly sampling the latent vectors from a normal distribution or a Gaussian distribution, you don't really have like the close correspondences.
So it's like, it's like, I think it's very similar to the autoencoder, I guess. I mean, autodecoder. So, you know, in the paper, their framework is based on the autodecoder, which uses a sampled latent code and then generate a data using this decoder. And by calculating the loss between it, you backpropagate this network and also learns this latent Gaussian distribution to represent this kind of data distribution. I didn't quite understand why you mean some kind of correspondence.
So I don't really understand what you're saying about when you're saying autodecoder. I don't really know what that term means, but if you think about a GAN model, you're comparing the distribution from a data set such that the model follows that distribution, right? So you don't really have a ground truth, but you have a distribution. But here you're comparing directly to the mesh positions. So it seems like condition. However, I don't see any conditions here because latent code is just random variables.
So so the latent code always changes and these are fixed. So you cannot have some Like one-to-one correspondence, you mean?
Yeah.
That is a good question, I guess. I never think of that while reading this paper, but as I thought was like, let's say there are some kind of sampled, some kind of distribution and train the network to make some kind of shapes. And I think this network, what this network is trying to do is to learn some kind of subspace of the distribution correspond to some kind of shape, not directly mapping the points to the points. I know the loss is directly calculating the loss between the generated ones and the ground truth, but I think the network has some kind of capability to average out those kind of thing. It's a.
So what is the goal of this paper again? So is it just randomly generating deformed model?
Yes. To make a parametric model.
So the user doesn't have any control, or does user have control?
Well, there are 2 points about the control, which I was about to tell in the later slides. But they have 2 ways to control. One is to change the shape based on point handle based control, and one is the semantic editing, which was similar to the interface scan. 맞나? Interface scan? Using
maybe
some kind of
maybe we can go on. It's taking too long.
Yeah. If I add a comment, this is my understanding, and then in the previous slide, my understanding maybe from my previous experience with other papers. So my interpretation of this was this: so hyper network will generate different parameters so that we have various caricature shapes eventually. But then if you just randomly generate a caricature shape, it may be sometimes a valid caricature, but then sometimes it may not be a valid caricature. So because of that, you want to be in the domain of valid caricature if possible with a high probability. And then you want to give a low probability to some extreme caricature cases. So latent code provide some sort of probability according to the Gaussian distribution. So that with a high probability, it stays in some domain of reasonable caricature that may happen. And then with a low probability from the Gaussian distribution, it will generate some extreme case of the caricature. I don't know it applies to this paper, but then usually from my previous experiences, that would be the way people approach this type of problems.
I think that would be correct, but I was super confused because of the loss functions, because they're comparing with the ground truth, because I don't see whether there could be a ground truth on this formulation.
Yeah, so there's a bit of a specific, so I can't answer to that, but anyways, okay.
Okay, so I'll continue for the presentation. So I spoke about the loss function, and for the training, it is, as I've spoken, using the ground truth is supervised learning, and they use 3D Caricatures dataset, which provides 3D caricatures, which shares the same topology. And for the template mesh, they use the template mesh based on the face warehouse, which provides various expressions in certain topology mesh. They mean out all those expressions to have some kind of mean face of that model and use that as a template mesh. And the weights, I mean the lambdas for the mean squared error and the regularization are as written in the presentation. And for the caricature reconstruction from 2D landmark, these are some kind of additional factors. I mean, 그걸 뭐라고 하지? I mean, additional thing you can do with this morphable model. So given a 2D image, you can fit this morphable model based on the 2D landmarks of the caricature. So they have a data set of 2D landmarks and the 2D caricature paired, and they try to optimize the latent code that fits the 3D, the key points projected onto 2D that matches the landmarks of the caricature, 2D caricature images. So given so minimizing function is as below, which based on the Z and the given the vertices, you have I believe this D should be the network that produces the deformed shape, and then you render it, project it onto the 2D plane to have a 2D landmarks, and this BI means the calculated 2D landmark from the caricature. So you minimize the distance between those two landmarks, and you have this fitted 3D caricature using this morphable model. And these are also another results, but I was not able to get the input image. You may find those details on their project page. And also they were able to do the semantic editing, trained with the same strategy with the interface scan using the semantic label dataset. And for this, actually, I didn't quite deeply look into it, but for my guess, I think they were having some kind of labeled data set of describing some faces of that morphed 3D, what is it? The 3D caricature data. So by finding the direction that no, maybe I think I didn't quite deeply look into it, so I'll just pass on for this part. Maybe I'll tell you the details on later on. And also they use the point handle based editing, which directly moving the vertices to other direction by user control. And the function below is the minimizing function to fit the point handle based editing. So this should be the generated 3D caricature, and this is the wait a second. Yeah. So delta is a displacement, Z0 is an initialization latent code, and PH is a handle vertex, and the H is the number of the handles. So for the handle number of the handles, you iterate throughout all those handle vertices to minimize the distance between the current 3D vertex and the user moved vertex. And I remember that I have put the result image right here somewhere, but it seems it has been gone away for some reason. Yeah, that is all for today's presentation. Thank you for listening, and you might ask freely for any questions.
If there is no question, we'll
I have
proceed to
one.
the-
We can
Okay.
Okay, so does the, what is it, p hat changes, or is it like a fixed template mesh throughout the whole process?
You mean on this loss function?
Not on that one, but the original formulation.
This
And
one?
maybe,
Yeah, p hat is a fixed position value. It's a template vertex position, so it does not change. It's a given input, and this is the parameter. And by using this parameter and the given input, you have an output of a displacement, and you add this displacement to the input vertex position to have a deformed shape. And you subtract between the ground truth vertex position and the generated vertex position. And yeah.
so I believe like the data set they use, what was it, like the face warehouse or something from Cow. I believe they have expression data set also. So I was wondering whether in their method they can change the template mesh such as to have certain expression, and then later on, like if you pass it through the network, the caricature would have the same expression or not. But I believe it's not the case then, right?
Yeah, I think it would not, work as we wanna do as it is. I think, yeah, finding an expression would be a job for this hypernetwork, I guess, by using some kind of semantic label editing, as I mentioned it here. But since I haven't deeply read through this part, so I won't be able to answer that question precisely.
I believe hypernetwork are mostly concentrating on the like exaggeration of the caricature faces. I don't, maybe they can handle expressions, but not sure about that really.
For their network, I believe, their data set contains various shape of the caricatures that also has a various expressions. So I think they did not separated the expression and the identity. So I believe they can just move around in the learned latent code, latent space to make those expressions. But I'm not quite sure about it since it's not precisely written in the paper. Maybe might missed it.
If you go to the slide that show the data.
This one?
Oh, yeah. So I hear. Oh, yeah. I see the description of calculated the mean face of face warehouse. So I guess from this statement, I think my interpretation that I explained before is correct. So basically, yeah, they have all this data set and then have a mean as a template mesh. So they want to give the higher probability there. And so they use the Gaussian distribution sampling.
Mm.
Okay.
Thank you for the answers.
And if there's no more questions, I will end today's presentation.